Hello, Astronomy. Mr. Janowski here. So this is part 2 of the chapter 2 slides. So the do now questions. What was Aristotle bad at? Aristotle was bad at physics. He had a lot of misconceptions about physics. And if you're taking physics or you took it last year, you know a lot about those things. He was bad at dentistry because he, for some reason, was convinced that women had fewer teeth than men. And he was also bad at feminism because the reason he thought that women had fewer teeth than men was because he was very sexist. And he thought that women were inferior and therefore must have fewer teeth. Um, he was wrong on both counts. Women have the same number of teeth as men, and they're not inferior. So he was bad at those things. So what was he good at? He was good at marine biology. Last time I told you, yeah, Aristotle gets credit for knowing he's the first person to record the idea that dolphins aren't fish, which I don't know why, but he noticed that, so good on him. Astronomy, he had evidence-based arguments that showed that the Earth was round, so good on him for that. And he did some things in philosophy that were probably worthwhile. So that's Aristotle. Then what did Eratosthenes do? So Eratosthenes determined the circumference of the Earth. And remember, he did it very, very well with like 0.4% error, which is just really good considering he did this in like the 3rd century BC with very crude tools. So yeah, here's Eratosthenes. Here's how he did it. Again, he was looking at the shadow from an obelisk in Alexandria where he lived, and he knew that this is on the summer solstice. On the same day, the sun was directly overhead in Syene, a town about 500 miles south of where he was. And on that same day, the sun was directly overhead, which means it cast no shadows. And if you were to look down at the still water at the bottom of a well, you would see the reflection of the sun because the sunlight would go straight down to the bottom of the well and then bounce straight back up. Any other day, it would be on an angle. He took that fact and a crude measurement of the angle here and did a little bit of geometry, alternate interior angles here and here, and then here and here, uh, and figured out, the circumference of the Earth. And this was a very long time ago. So good on him for that. So his whole argument is based on the idea that the sun must be very far away from the Earth. Because if the sun is very far away from the Earth, in this picture, the sun would be way off to the right. If it's very far away from the Earth, the rays of light from the sun hitting the Earth would be pretty close to parallel. Would not be true if the sun were fairly close. If the sun were fairly close, the rays would devolve a little bit, and then you can't say parallel lines and alternate interior angles and things like that. So he knew that the sun was very far away. So how did he know that? He knew that because a little before him was this guy Aristarchus of Samos, who did a few things. He calculated the relative distances to the moon and the sun, and from that, he figured out that the sun was really far away, which was surprising to people at the time. They didn't realize that the sun was much further away than the moon. And then after that, he figured out the relative sizes of the Earth and the moon and the sun. So in both cases, the relative things, the relative distances to the moon and the sun. He didn't know how far it was from the Earth to the moon or from the Earth to the sun, but he knew how those two distances compared to each other. And he didn't know the absolute size of the Earth or the moon or the sun because Eratosthenes hadn't figured out the absolute size of the Earth yet. But he did know how the size of the Earth compared to that of the moon and how both of these compared to that of the sun. Now, here's the catch. His estimates for these things were not very accurate because his measurements were pretty bad. It's not his fault. He was working a very long time ago, and his instruments would have been very, very crude. So he got the wrong answers in terms of their value, but his answers were in the right direction. And his technique was sound, meaning his reasoning made sense. It worked. And if he had more accurate measurements, it would have worked very well. So here's how he did this. First of all, estimating the relative distance Earth to the moon compared to Earth to the sun. So he knew that during the first quarter moon, when he could see, a quarter of the moon, he could see half of the moon that was lit and facing the Earth. He knew that the angle from the Earth to the moon to the sun had to be 90 degrees. That's true. So he knew that. He knew that if the sun were relatively close, as it is in this picture, if this is a 90-degree angle, this angle would have to be much less than 90 because the interior angles of a triangle add up to 180? That's geometry. We don't need to know that. You should know that, though. But yeah, that's his idea. So what he did is he actually measured this angle here, and he saw that it was actually very close to 90. A little bit less, but very close to 90. So he took that. He did a little bit of geometry, a little bit of trigonometry, and he figured out, okay, if this angle is just a little bit less than 90, he could figure out the ratio of this length here, Earth to the moon, to this length, Earth to the sun. And he did that, and he calculated that the sun is about 20 times as far away from the Earth as the moon is from the Earth. And the actual answer is 400 times. So he was off by a factor of 20. He wasn't very close, frankly, because he couldn't measure this angle very accurately. He knew that it was close to 90, but he couldn't get the angle exactly right. So yeah, he got the wrong answer. So here's the thing. Even though his answer was off by a factor of 20, his technique was good. It made sense, and it would have worked. And even saying the sun is 20 times as far away from the Earth as the moon is was still important because people didn't know that at the time. They thought they were about the same distance away. So that by doing that, yeah, he was wrong, but he was in the right direction. So now that he knew that, this gave him a way to estimate the relative sizes of the sun and the moon. So remember that during a total solar eclipse, the moon moves in front of the sun, and the moon appears to be just about exactly the same size as the sun. So he used a little bit of a geometric argument here. And he said that, well, the moon and the sun have the same angular size, which means if you were to measure the angle, if you were to look at the moon and point at one side of the moon and then point at the other side of the moon and measure the angle between your fingers, that would be the angular size. Because you can't measure the absolute size of the moon just by looking at it, but you can measure the angular size. What angle does it subtend? And so if the sun and the moon appear to be the same size in the sky, they have the same angular size. And if he knew how this distance, Earth to the moon, compared to this distance, Earth to the sun, then he knew how their relative sizes compared. So again, because he was wrong with how these numbers compared, he thought it was 20 times when it's actually 400 times. Yeah, he got the final answer wrong, but he was still in the right direction. So he said, yeah, if the sun and the moon have the same angular size, but the sun is 20 times as far away, the sun must be 20 times larger. Again, the sun is actually 400 times as far away as the moon, and it's about 400 times larger. So he was a little bit off. Then he did a different thing, and he was able to calculate the relative sizes of the Earth and the moon. Again, not the absolute sizes, just how their sizes compare to each other. So he did this by watching a lunar eclipse. And he knew that during a lunar eclipse, it takes about an hour for the moon to move one full moon width across the sky. So he measured the length of time for a lunar eclipse, how long it takes the moon to go across. And he made an assumption that the Earth's shadow is about the same size as the Earth. And he was able to figure out that the moon's diameter must be about 0.35 times the diameter of the Earth, or 35% the diameter of the Earth. So he was a little bit off here. His reasoning was a little bit flawed because he didn't realize that the shadow of the Earth actually narrows because the sun is so much wider than the Earth. It narrows. It's a geometry thing. So 0.35 times wasn't the right answer. 0.27 times is the right answer. But he was in the ballpark on this one at least. So now he knows the relative size of first moon to the sun, and now he knows the relative size of the Earth and the moon. So it doesn't take much from there to figure out the relative size of the Earth to the sun. So using his numbers, he estimated that the sun must be about 7 times the diameter of the Earth. And so he figured that if the sun is that much bigger than the Earth, then maybe the sun doesn't go around the Earth. Maybe it's the other way around. Maybe the Earth goes around the sun. Maybe the sun is at the center, and this is called heliocentrism. And he was exactly right about that. Yeah, the Earth does go around the sun. However, nobody believed him. People weren't ready to accept this idea. So we were stuck with the old idea, which is called geocentrism, geo for Earth, so the Earth at the center, which is the idea that the sun and all the planets and everything else goes around the Earth. So why did people not believe his idea? It wasn't because they were stupid. They had a good argument for their idea, which we will see now. Their idea starts with the idea of parallax. So what parallax is if you close one eye and you hold your thumb out in front of your face, and you use your thumb to exactly, eclipse, exactly block something in the distance. So, I mean, it could be something across the room. Um, and then you open that eye and then close the other one, something weird happens. So you can do that now and see what's going on. Take your thumb, hold it in front of your face, look with one eye, block out something on the other side of the room, and then switch eyes. And when you do that, you will see that your thumb appears to move, which isn't what's actually happening. So your thumb isn't moving. The thing itself isn't moving. What's moving is you, in a sense. By switching from one eye to the other, you're switching where your position is. So you're moving just a little bit, just a couple of inches, one eye to the other. And doing that is making your thumb appear to move compared to the background things. That is what parallax is. Parallax is the apparent shift. It's an apparent shift. It's not real in position of foreground objects, which again, they're not actually moving, compared to the background objects when the observer moves. So Aristarchus's contemporaries, they said, okay, well, if the Earth is moving, then we should see parallax. Because if, this is Aristarchus's model, sun at the middle, Earth here, going around the sun. Well, there should be nearby stars. Some stars should be closer than others. So here's a nearby star compared to background stars. If the Earth is going around the sun, then sometimes it should line up this way, and this star should appear next to these stars in the background. And then 6 months later, when the Earth is moved over to here, it lines up differently. So now this star appears lined up next to these stars. So that is parallax applied to stars. They said if the Earth is moving, we should see that, and we don't see that. So their logic is also correct. However, they were missing one important piece of information. The important piece of information that they were missing is that all of the stars, even the closest ones, are incredibly far away, really, really far away. So this picture is nowhere near to scale. In fact, the distance from the Earth, from here to here, so this is the diameter of the Earth's orbit, the nearest star is 100,000 times greater than this distance. So again, this picture is not drawn to scale. So if the nearby stars are that far away, there will be parallax, but the parallax is so tiny that you can't measure it without extremely precise telescopes, extremely good telescopes. So it was there, but they couldn't see it because they didn't realize that the stars were as far away as they were, much, much further than the sun and the moon are. So how much further away are they? The absolute closest star to the Earth, and therefore the star with the greatest parallax, is Proxima Centauri. The parallax of this is about 0.8 arc seconds. So what is an arc second? If you take a circle, a circle is 360 degrees. So think of how tiny a single degree is. 1 degree is very small. If you chop that 1 degree up into 60 even smaller angles, each one of those angles would be an arc minute. And if you chop each one of those arc minutes up into 60 equal smaller angles, those will be the arc seconds. So degrees are small, arc minutes are tiny, arc seconds are tiny, tiny. And the biggest parallax you can hope to see in any star is less than 1 arc second. It's only 0.8 arc seconds. So to put it in perspective, that's the equivalent of a sideways shift of 2 centimeters from more than 5 kilometers away. So 5 kilometers is about 3.1 miles. So imagine looking at something that was 5 kilometers away from you, and then it moves 2 centimeters to one side. You wouldn't be able to detect that with your naked eye. So in Aristarchus' time, we didn't have telescopes at all. And in fact, we wouldn't have telescopes that were sharp enough to measure this parallax until 1838. So Aristarchus was 2,000 years too early. So nowadays, astronomers can use parallax, and we do, to determine the distance to nearby stars. It only works for the nearby stars. If the stars are too far away, the parallax that is there is too tiny to even measure with our best telescopes. But for fairly nearby stars, we do actually use parallax now to determine their distance. The other argument is another parallax-based one, although a little bit different. So notice, okay, the Earth is here in May. A few months later, the Earth is here in October. So if you're looking at distant stars, you should measure a certain angle from one star to another, so the red one to the blue one. And when the Earth is here in May and a little bit further apart, this angle should be different than the angle you measure here. So the white angle should be different than the yellow angle, which is where the Earth is in October. So this argument is also true, but again, the stars are so far away that the difference in this angle is so very tiny you have no chance of measuring it because this picture is not to scale. So yeah, there is a quiz on Google Classroom. So take the quiz, and then we did a Kahoot. And that was it for the second part of the slides. So hopefully you found that helpful.